All right, so at the beginning of the semester, I introduced the basics of chemistry. Because you got to build on something. Everyone has to understand the same things in order to get to more advanced topics. Then in the last 3 weeks, we've been talking about the language of chemistry. Please, your computers need to go away. Your computers need to go away. We don't need the computers for a while. All right? So, we learned the language of chemistry. So that was the ionic language and the molecular language and the acid language. Now we are ready to put it all together and dip our toes into water. Is the water contaminated? Is the water bad for us? Is the water safe? There's all sorts of signs here in Oak Ridge that say, don't be swimming in this water. Because the water is contaminated. With what? With things that have dissolved in it. And in some cases, it's things that have not dissolved in it. So, I need to build this content. I need you to understand certain things in order to really, really delve into the practical side of chemistry. So the problem ahead, as we saw in the Flint River, the water was too high in lead levels. What does that mean to be too high? So let's spend some time understanding how things dissolve in water and what factors could possibly affect how much stuff dissolves in water. So today we're just going to hit the basics and start jumping from there. So let's review. What is a solute again? A, stuff that gets dissolved. B, stuff that does the dissolving. B, A, which one is it? No. A, the stuff that gets dissolved. Stuff that is dissolved in another substance, which means what is a solvent? The stuff that does the dissolving. So, what is solubility? The maximum amount of solute that can be dissolved by a solvent. Now, you may or may not understand this. So I'm going to use an analogy to help you understand. You've been to an elevator. Everyone here has been to an elevator, and there's usually a sign that says capacity. Okay? What that means is the federal government, who oversees the safe operation of elevators, have decided that as long as you stay below this weight, the elevator's just fine. You go above the weight, and there's trouble. You've been to pools. Even pools have capacity signs. Okay? Now, imagine going to Myrtle Beach, or any beach at all. Myrtle Beach, it's an older beach, so it has a lot of old signs. I mean, its heyday was in the 1950s when we went neon crazy here in America. So I remember driving down that major corridor in Myrtle Beach, and there's signs everywhere. There's hotels on the left, which are beachfront. There's hotels on the right where you have to cross the street. Everywhere you see the hotel name in lights. And then below the name, there's usually the word no and vacancy. As I was driving down that road, I noticed that sometimes the hotel had both signs on, no vacancy. Sometimes it just said vacancy. What does that mean? Well, for all hotels, due to how much living space you have, the federal government allows you can have a certain number of people in your hotel. Usually it's a whole lot simpler than that. You can have a certain number of people per room in the hotel, and you have a certain number of hotel rooms. So, typically, if the hotel is completely full, they put the no in front. They light up the no in front of the vacancy sign, telling you, don't even bother. We're full. We can't have any more people. If there are rooms available, they will only light up the vacancy sign, meaning, come on in. We've got room for you. By the way, on a practical note, because I met a fellow who was a hotel employee, is a hotel ever completely full? The answer is no. When they say they're full, they're not full. They usually keep back 1 or 2 rooms. Can anyone tell me, practically speaking, why? Raise your hand. Connor? For the workers? No. No. But that's a possibility. That's good. Seth? Yeah, what happens if who's ever gone to a hotel room and the air conditioning isn't working, or there's a small flood around the sink, or the toilet isn't working? Who has that ever happened to? Okay? What did the hotel people do? They switch rooms. So they usually keep back a room or 2 just in case one of their rooms go bad. Okay? It has nothing to do with chemistry. I just thought it was interesting. There you go. Practical. All right? So, the federal government makes these rules for how many people can be in the hotel. That capacity is the rule. In chemistry, how much solute can dissolve in a certain amount of water is the capacity. So think of solubility as how many people can be in the hotel at one time. How much solute can dissolve in the water at one time. So solubility is that capacity limit. Solubility is at capacity limit. By the way, a few years ago, there was a hurricane in Savannah. The people that were staying in Savannah had to flee. Get out of the way. So, Myrtle Beach is just up the coast from Savannah. Myrtle Beach was going to be okay. It wasn't going to hit Myrtle Beach. So a lot of people fled up to Myrtle Beach. They needed a place to stay. Well, Myrtle Beach got completely full. Because of the emergency situation, the federal government allows, under emergency situations, for hotels to host more people than they should be able to. So at that point, under an emergency, they're going to bring out the cots and put cots in their dining area, put cots in their hallways, in order to house people temporarily in an emergency situation. So we have, with hotels, 3 possibilities. Number 1, we have a possibility where there's plenty of room. Number 2, we have a possibility where it's full. And number 3, we have a possibility when there's more people in the hotel than you should normally have. In the same way, we have the 3 possibilities when things dissolve in water. Unlike hotels, you can actually change the capacity of water. So it's not like, can you imagine a hotel where the hotter it got, the more rooms appeared? Or the colder it got, the more rooms disappeared. Okay, that would be analogous to this situation. Temperature can actually free up more room to dissolve in water. So more stuff can dissolve in water if you increase the temperature. In the case of these soda drinks, you can only dissolve so much fizz, carbonic acid. You can only dissolve so much fizz in water at our pressure. So what do? They pump a lot of air into this bottle before they seal it in order to force the carbonic acid to stay dissolved. So pressure can affect the capacity. And of course, you build a bigger hotel, add more rooms, that can also change the capacity. Add more water, you can dissolve more stuff. So, unlike real hotels, where temperature really can't change the capacity or pressure or the amount of solvent, water can be changed. How much water can dissolve if water is a hotel room, how much water can take people, can be changed by these three factors. Okay, so what happens when the solute hits its limits? It appears as if no more solute is being dissolved, but in reality, there is. So copy these notes down, and then I'll explain it to you using a story, a true story, involving my friend Jeff. Actually, as luck would have it, we have spring break coming up, and I just asked him, hey, do you want to have lunch here in a couple weeks? Because I haven't had lunch with him in a long time, so he is still my friend. But, and I hope he never hears this lecture, he used to be Jeff. In my heart, he used to be Jeff, the Yankee idiot. Because he was from up north. When I first met him, he had recently come down here to the south. And he had this, Southerners are backwards and are idiots and are bumpkins, and Northerners are better. And I really, even though technically I'm not from the South because I grew up in South Florida, and South Florida is not really the South, but I had been living in the South for a while, and I really appreciate the South. I think Southerners have a lot to contribute, and Southerners are superior chemists. Moonshine, that's chemistry. And sweet tea, that's chemistry. Okay, so we went out to dinner with he and his wife, my wife and I, he and his wife, and he made a big stink with the waitress when she asked, what would you like to drink? I said, water. My wife said, sweet tea. His wife said sweet tea. He said, I want unsweetened tea. I do not want sweet tea. I want unsweetened tea. So I thought to myself, okay, he doesn't like sweet tea. So she comes back with the drinks, and I noticed him reach for the sugar packets, and now I'm confused. If you order unsweetened tea, why are you trying to sweeten your tea? And he said to me, and that's what I asked him. And he said to me, I think Southern tea is way too sweet. I go, okay, whatevers. So he adds three packets of sugar to his unsweetened tea. And he mixes it around, and it all disappears because the water had plenty of room for it. It had not reached its capacity yet. He takes a drink. I watch him take a drink, and he makes a funny face. Obviously, it wasn't sweet enough for him. And I'm beginning to think, 3 packets? I mean, really, how much more sweeter can you make it? So he reaches for another couple, 2 packets, opens, pours it in there. He stirs. I now notice a pile of sugar down at the bottom, which to me says, you've reached your limit. At that temperature, no room in the inn, no vacancy. You cannot dissolve more sugar. So he takes a sip. It's not good enough. He reaches for more sugar. I go, stop, Jeff, stop. And I explain this to him. I go, Jeff, you are a marketer. Marketing is your thing. I don't know marketing. Chemistry is my thing. This is chemistry. You have now a saturated solution. That solution contains more sugar than it can possibly hold. That is why there's a pile of sugar down on the bottom. If you add more sugar, you are going to add to that pile. You're not going to make it sweeter. To prove the point that he could, which he couldn't, but he said he could, he added 2 more packets of sugar. Now you have a pile of sugar this thick down on the bottom. He takes a sip, and guess what he decides at that point? Now it's sweet enough. It wasn't. It was just as sweet as it was before. Why? Because I understand chemistry. He saturated it. It's like you are cleaning your mom's car because you're being nice, and you're drying the car because you don't want any water spots on there, and you have a sponge, and you're using the sponge to pick up the water, right? To dry it. And ever so often it gets to the point where the sponge leaves behind the streak What do you have to do? What's happened? What's happened to the sponge if it's leaving streaks behind? It's full of water. So what do you have to do? You have to squeeze all the water out. It has become saturated. In the same way, if you add too much solute, you could saturate the water, and there's just too much there. He saturated that water sugar solution. Now, in reality, there is dissolving going on. He's right. But for every crystal that dissolves, somebody has to come out. That's what we call equilibrium. Imagine this room was full of people, so full that we are all, and this just irritates me just thinking about it. We're all touching each other. We're all in each other's space. There is no room in this room. Okay, we open both doors. TA's over there staring at the lab, and there's people behind him. He is just inside the room. And over here, Jackson is staring out. He is just inside the room, barely. There is no room. He can't back up even 2 inches. What happens if I was to bring somebody else in and shove them right into Jackson? Can I shove them into Jackson? Yeah. What happens to TA as he is standing right there at the edge of this room? He gets pushed out. That is equilibrium. That is equilibrium. It can happen, but for everyone that dissolves, somebody must come back out. So, if you were to stir and give it enough time, will it dissolve? No. Once you reach equilibrium, once you have reached saturation point, you can't dissolve anymore. So you will see a pile of sugar down at the bottom. That's what was happening with Jeff. He had reached its limit, and now he could not dissolve anymore. Yes, he could, but we can't see it happening. We would just see a constant pile of sugar down at the bottom. Why is temperature important? Because for most solids, the hotter the water, the more you can dissolve. That is the secret of Southern sweet tea. We take a ton of water, we get it really, really hot. We get it to the point of boiling, and then we add several bags of sugar to it, and it'll dissolve it. It'll dissolve. Water can dissolve a lot of sugar at room temperature. I'm sorry, at almost boiling point. You can't go beyond boiling point. Why can you not go beyond boiling point, my friends? Why is 100 degrees the limit for water? What? Okay, evaporation actually happens before 100, so evaporation is the wrong word to use, but you are on the right track, Lindsay. It becomes vapors. It boils. At 100, it's going to turn into a gas. You can't dissolve anything in water gas. So, the reason why the 100 is the limit is because you can't go beyond 100 with water. Iced tea, hot tea. Which one can hold more sugar? Hot tea. There is a chart that can help us determine how much stuff can dissolve, and that is called a solubility graph. I'm going to spend the rest of the period or this lecture explaining how to use this solubility graph for 2 reasons. Number 1, because it's important in chemistry, and number 2, because many of you guys are going to be taking the ACT exam soon, or you already have, and you realize that the science portion is really not the science portion, is it? It has very little to do with science. It has everything to do with being able to analyze graphs and tables, right? Table and graph analysis. Am I correct? That's all there is to science. It's not like it's a review of how much you've learned. It's really, can you identify something from a graph? So, solubility curves. What you have on one side is how much water, how much you can dissolve in 100 grams of water. So it's per 100 grams of water. And then on the other side, you have its temperature. So how many people are in the hotel? or can be in the hotel versus how hot it is. If you could somehow affect the size of a hotel with heat. So, let's see if we can't answer some questions. And yes, I know the notes already have the answers, so let's make sure we understand why those are the answers. Okay, so KNO3 is this line right here, right? Potassium nitrate. If I had taught this to you 4 weeks ago, you would have said KNO3. What's that? But now you know it's potassium nitrate. At 0, how much can you hold there? About halfway between 10 and 20, right? I said 15 grams. But if Lindsay were to say 14 grams, I would accept it. If Carl were to say 16 grams, I would accept it, because with this graph, you really can't tell the ones very easily. But it looks like it's about halfway. Any questions? On 0. What about 50? So you go 40, 60, so 50. Go up, go up, go up, go up, go up, go up. There, go around, go to the left. And if I had a straight edge, I would probably get it closer. It looks like it's around 85, doesn't it? And at 100, at 90, I'm sorry, at 90, go up, 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 and over, and it looks like it's reached its limit with 200 grams. So those are its capacity. That's how much stuff it can dissolve at those temperatures. Notice that for potassium nitrate, it really goes crazy. Potassium chloride, it goes pretty high. Sodium chloride, though, check out sodium chloride. Very interesting. On the Earth, water does not get colder than 0, and it doesn't get colder than 30. Actually, that's not true. It can get colder than 30. It doesn't get warmer than 40. What can you tell me about how the solubility of sodium chloride will change from 0 to 40? It doesn't. That's actually very important, especially if you're a big fan of Finding Nemo. Why? Well, anybody out there have a saltwater tank at home? Saltwater fish? How about freshwater? Freshwater? Okay, freshwater by and large is going to be much more popular. Saltwater is going to be far more interesting because you're going to have a whole lot different animals, and they're colorful and very interesting. Okay, what? What? Yes, she is absolutely correct. The reason why more people do not have saltwater tanks, even though they're far more interesting, well, 2 reasons. Number 1, the fish by and large are far more expensive. And number 2, it is very, very, very difficult to take care of. It's a day-to-day thing. Fresh water, you can just let it go, and ever so often add more water. Salt water, you better check every day, because if it gets too salty, all the fish will die. If it's not salty enough, all the fish will die. So, is it significant that salt does not change its solubility as you go from the hottest part of the ocean to the coldest part of the ocean? Yeah. Think about Finding Nemo. Nemo was lost. Marlin, his dad, had to go find him. He went from warm, shallow seas down to the Marianas Trench, which is as cold as you can get, back up to warm. And he never died. Why? Because the salt content didn't change. Fish are very, very, very sensitive to changes in salt. Now, this is called this weirdness, and salt is the only thing that will do this. And guess what is the most of the salt in water? Like NaCl. This is called the anthropic, an example of the anthropic principle. There are like 100, actually anywhere from 80 to 100 things about the Earth and about the solar system and about our galaxy that is finely tuned for life. And if it was just a little different, life could not exist here on Earth. For example, if the Earth was just a little bit closer to the sun, life could not exist. If the Earth was a little further away from the sun, life could not exist. If the amount of oxygen in the Earth was a little higher, life could not exist. If it was a little lower, life could not exist. This goes on for about 100 different topics. So this is studied and this is marveled at. Imagine you were to go into a control room and there's 100 dials. And in order for you to exist here on Earth, every dial has to be perfectly placed. So this has led scientists to conjecture, how can it be so perfect? Two possibilities: God or the multiverse. And I bring it up because Doctor Strange and the multiverse is coming up. So the multiverse theory has never been proven. There is no evidence. But it tries to get away around there being a God. Because, most people would say, well, somebody adjusted all the dials. So the multiverse theory tries to explain it by saying, well, yeah, there's just a teeny tiny chance that this could have all happened by accident. So what if we have an infinite number of universes where in some of them we exist and some of them we don't? So in an infinite number of universes, by chance, sometimes all those dials are perfect. And life can exist. And in most of the universes, there's no life. So the whole multiverse theory comes from this weird anthropic principle. Any questions? All right. So, what is the solubility curve for sodium chloride like? It's almost a straight line. And if that wasn't the case, life could not exist here. So, let's talk about three terms that are going to be important to us. Saturated. Saturated is, that's it, you've hit the capacity. If you are on the line, you are saturated. That is your capacity. That is your capacity. So, if you're holding as much as you can, and you can't hold any more, you are saturated. Unsaturated means, no, you can hold more. You can hold more. There is more room in the hotel. Bring more people in. Plenty of room. So, how can you tell if a solution is saturated or unsaturated? It's going to look the same. Go to it, add a few crystals. If it dissolves, unsaturated. There was room. If you see a pile down here at the bottom, ooh, saturated. Saturated. Did I go too fast? I'm sorry. Now, so saturated means the hotel has no more room. Unsaturated means, no, there's room. Supersaturated, in our analogy, was where the hotel was given special permission to allow more people in it than it could possibly hold. This is special permission. This is weird. There shouldn't be that many people in that hotel. So once the emergency is over, they have to come out. So for example, this beaker is supersaturated. Add one crystal to it, and then all of a sudden you see a bunch of crystals growing. That meant it was supersaturated. Not every crystal can do this. Basically, there are some crystals that forget what they look like when they dissolve. Sugar is like that. Sugar forgets what it looked like. So you have to remind sugar of what it looks like. Once you remind sugar of what it looks like, the sugar starts coming back out. Sodium acetate, which is the salt in salt and vinegar chips, is also like this. This is probably sodium acetate. It forgets what it looks like. So when you remind it by giving it one little crystal, it goes, hot dog, that's what we used to look like, and all the extra emergency crystals come back out. So, in review, if you add sugar to the water and it disappears, unsaturated. If you add sugar to the water and it forms a pile down at the bottom, saturated. If you add sugar to water and crystals begin to grow, super saturated. Two examples of supersaturated solutions. This is honey. My wife does not know this, but I ruined it. I was wondering, because I know that honey is supersaturated. It is a water that contains way too much sugar. So I opened it up and I took some of the crystals of sugar that had dried on the edges and I kind of kicked it in, and the next day you had this pile of sugar up on top and there was water above it. So over time the water has evaporated. I brought it to school in order to show my students at that time. So there used to be water, kind of like really sweet water, but it was still mostly water up top. And over time it has all evaporated, leaving behind all the sugar that came back out. So honey is a supersaturated solution. Now I have no idea how the little bees can do it. No, it's going to be really super sweet. Ever made rock candy? Rock candy is a supersaturated solution of sugar. Take a stick, put some crystals on the stick, and watch the thing grow. Where on the solubility chart are you going to find unsaturated solutions? Below the line. Below the line. What about saturated? On the line. On the line. And supersaturated? Above the line. So, by just knowing where you are on the solubility chart, you can know whether you are unsaturated, saturated, or supersaturated. Make sure you add this to your notes. If you are above the line, super. If you're on the line, saturated. If you are below the line, unsaturated. We're almost done, gang. I know this is a longer lecture than normal, but I thought it was interesting. I thought there were some aspects of this lecture that are very interesting and practical. Okay, we got it? All right, let's practice some of this because you'll need it for the worksheet. If you dissolve 80 grams of KNO3, 80 grams of KNO3, so you go to 80 and put a dot there, at 70 degrees. So where does this intersect? Of KNO3. So this point, where is it? On, above, or below the line? Below the line. So this would be unsaturated. All right. Okay. So notice that they said 80 grams of KNO3 dissolved. This is how much is dissolved. 80 grams. Okay, at 70 degrees. 70 degrees. So where do both points intersect? Right here. This is the line. Is that line below, on, or above? Okay, good. Let's try another one. 80 grams at 90. KCl. Is it super, sat, or unsat? Yeah, it is above the line, above this line, so it is super. It's holding more than it should. And finally, 60 grams, 40 degrees, KNO3, unsat or super? Sat. So, let me try one more time. Draw this illustration. Give me 3 beakers with water on them, in them. 3 beakers with water in them. Add some crystals, and they begin to pile up down at the bottom. Add some crystals, and you see a bunch of crystals growing everywhere. Add some crystals, and they disappear. Okay, so one of these beakers is going to be saturated, one will be unsaturated, and one will be supersaturated. Sarah, which one is your unsaturated? The third one? Is that what you said? You are correct. Azariah, which one is supersaturated? You are correct. Jackson, which one is saturated? You reckon it's the first one. That is correct, since that's your only other choice. All right, let me show you using a video, and then we're done. All right, so you have a test tube. You add some water. You add some sugar, and watch what happens. It just disappears. So that means it's unsaturated. Add some sugar, and it seems to not want to dissolve much, and it's piling down at the bottom. So that is supersaturated. By the way, have you ever played around with these little packets called hand warmers? Okay, there's a little disc in them, and when you pop the disc, it turns into a solid, and it gets really, really hot. That's this stuff. It's sodium acetate. It's the stuff that's added to. Is that it? Pass it around. Does it become? Is it a liquid now, or is it all solids? Is it a liquid in there? Oh, that may not be this stuff. If it's like a liquid, and I'll bring one out, then it's this stuff. Watch what happens. When you break the disc, it pops out some crystals that are inside the disc. But in this case, they're going to go in with some tweezers. They're going to get one little crystal. One little crystal. There you see the one little crystal. And watch what happens. all the crystals that should be out come back out at one time. All right. We're done.